So this video talks about some old stuff and some new stuff, focusing on the chemical formula and the way we show it, the way we write it, the way we can figure it out, and so forth. So there's a lot of different ways that you can show the same chemical formula, especially for molecular substances. So if you remember, the molecular formula is simply just a list of what the elements are and how many. Sometimes you wind up with what's referred to as a condensed structural formula, which shows you a little bit more detail about the structure than the molecular formula does. So here you just know you have two carbons, but here you can see that they've written the carbons separately. The first carbon has 3 hydrogens attached to it. The second carbon has 2 hydrogens attached to it. And then you have an OH, which again doesn't show in this molecular formula, although this version of the molecular formula does show that. You can also get more detailed with structure by taking a look at the Lewis structure, which, if you remember, shows the pairs of non-bonding electrons, or the structural formula, which shows no non-bonding electrons. And then you have all sorts of other versions that, like I said, mostly for organic molecules, you're going to see this. So the skeletal structure obviously shows no carbons here, but every time you have a point, that point represents a carbon and however many hydrogens you need to have a total of 4 bonds. If there's a double bond somewhere, you will see 2 lines coming down like that for a double bond, and then again, however many hydrogens you need for 4 bonds to each carbon. You've got the 3-dimensional shapes, which shows the angles trying to emulate the tetrahedral. 3D perspective we're not ever going to draw because that's pretty hard, but you can see that it is trying to show the angles. If you have a very bold bond, that means it's coming out towards you out of the plane of the paper. And if you have the dashed lines, those indicate that those bonds are actually going back into behind the plane of the paper. And like we did in the ball and stick kits, the model kits last year, you can do the ball and stick structures. And they also have something called space filling models. We haven't really worked with those at all. All right, so all of these different perspectives you should be familiar with for molecular substances because you're going to see them all. Even though AP Chem is not really focusing too much on organic chemistry, you probably learned more in first year chem than you will be using this year. Some things, for example, the alcohol with the OH is going to come up a lot, so it's good to learn those things and be able to recognize these different structures. All right, if we jump to ionic substances, it's a little easier. Really, the only thing you have to worry about is the formula unit. So not molecular formula, the formula unit. That's not something we emphasize too much in first year, but you're going to see it come up a little more often in AP. So the formula unit is the lowest whole number ratio of cations to anions. So NaCl means that for every 1 sodium, you have 1 chlorine. But if you remember, ionic compounds aren't individual molecules, they're alternating, they're lattices, crystal lattices of alternating cations and anions. So here is what really a sodium chloride looks like. But if you were to count, the ratio of Nas to Cl's should be 1 to 1. You can also see space-filling crystal lattices, but both of them are emphasizing the fact that it's not just 1A with 1 Cl, it is proportionally 1 to 1. All right, so let's take a little a closer look at formulas, and this is some new stuff now. So the empirical formula, like what you saw with the ionic compounds, the empirical formula is always the lowest whole number ratio of atoms in the compound. So ionic compounds are always empirical formulas. Molecular formulas which you're going to see in molecular substances, are really the true number of atoms of each element in the compound. So here's an example of the difference. So the molecular formula is equal to the empirical formula times some integer. So for example, if the molecular formula is C6H6, the empirical formula is actually, you reduce that, CH is the smallest whole number ratio to the sixth. So like I said, the empirical formula is CH, but the molecular formula is C6H6. And as I mentioned before, formulas for ionic compounds are always empirical formulas. They're always the lowest whole number ratio. Sodium chloride, magnesium chloride, aluminum sulfate, potassium carbonate, always the lowest whole number ratio. 1 to 1, 1 to 2, 2 to 3, 2 to 1. All right, so formulas for molecular compounds might be empirical, the lowest whole number ratio, or they might not be. So a if the molecular formula is H2O, the empirical formula is still H2O. So here's where they're the same. However, you have something like glucose, C6H12O6. Glucose can actually be reduced to what? CH2O, 1 carbon, 2 hydrogens, 1 oxygen. And then if we look at something like sucrose, C12H22O11, initially you think, oh, that's got to be simplified. You have to be able to make that smaller. But no, with that oxygen having only 11, the molecular formula is the same as the empirical formula, so you can't reduce that one. So even though it can be different, it doesn't necessarily have to be different. All right. Other new stuff, the idea of percentage composition or percent composition of a compound is really the amount that each element contributes to the mass of the whole thing. So here's a very straightforward calculation, if you will. The percent composition of an element is however many atoms of the element you have. You know, C6H12O6, you have 6 carbons, times the mass of a carbon, which would be 12, and then divided by the whole molar mass of the substance, which would be 6 carbons plus 12 hydrogens plus 6 oxygens added together. And then to get percent, you times 100. So it's a pretty straight formula. It's pretty intuitive. But here's an example just to make sure that you're comfortable with the idea. This is not something we did in first year, but I think it's something that you can pick up pretty quickly. So first thing we want to do is figure out for magnesium carbonate what the molar mass is going to be. So you've got the mass of 1 magnesium, the mass of 1 carbon, and the mass of 3 oxygens gives you 84.32 grams. The percent composition then of magnesium, since there's only 1, you're going to take that mass times 1 divided by the whole thing times 100. So magnesium actually is responsible for 29, give or take, percent of the mass. Carbon is responsible for 14, and then because there's 3 oxygens and all the masses of the different substances are comparable, oxygen contributes the most, more than 50%. So calculating percent composition is pretty straightforward. Now you can go the other way as well. Oh, also note that the masses or the percentages should add up to 100 or something close to it within rounding. If you have the percent composition, you can use it to find the empirical formula. And so remember that the empirical formula is the smallest whole number ratio. So what we're going to do, a couple of rules here, and then we'll do an example. So the easiest thing to do is base your calculation on 100 grams of compound. Because if you do that, then the percentages really become masses, and they're easy to work with. Once you know how much mass of each element you have, you're going to determine the number of moles of each element. Again, if it's based on 100 grams, it's easy to go from percent composition to empirical formula. Once you know how many moles of each element you have, you're going to divide each value of moles by the smallest number, because you want a mole ratio. You don't want a mass ratio, you want a mole ratio to write your empirical formula. So you're going to divide all those moles by the smallest one. And then if you have to, you may not have to do step 4 here, but if you have to, you're going to multiply each number by an integer so that you get all whole numbers. So here's an example. So adipic acid is 49.3% carbon, oxygen, and hydrogen. You can see by mass. What's the empirical formula? So we're going to treat these percentages as masses, and we're just going to convert them from grams into moles. So 49.32% carbon becomes that many grams of carbon. Converting it into moles gives you that many moles of carbon. Hydrogen and oxygen, you do the same way. So I have these moles of each of the elements represented. Next thing I'm going to do is divide each of those moles by the smallest value. And if you looked back, it was hydrogen that was the smallest. So we're going to take the moles of carbon divided by the 2.74, because that was hydrogen. Oops, nope, sorry, that was oxygen, not hydrogen. So we're going to divide everything by the smallest number of moles, which was, again, oxygen, my bad, not hydrogen. And look at the numbers that you get. You get 1.5, you get 2.47, which is essentially 2.5, and you get 1.0. Now, so if we were to write the empirical formula, C1.5, H2.5O1 makes no sense. You've never seen a formula with decimals. So what we need to do is we need to convert these 4 decimal numbers into whole numbers. So how do you get rid of 0.5s? Multiply everything by 2. So you multiply the carbon by 2, you get 3. Hydrogen by 2, you get 5. Oxygen by 2, you get 2, which means our empirical formula for the substance is C3H5O2. Once you know the empirical formula, then you can figure out the molecular formula based upon what the molar mass is. Okay, so first thing you have to do is find your empirical formula. Then find the molar mass of the substance, assuming it's going to be given to you. You're going to divide the molar mass of the substance by the empirical formula and figure out how many times that formula goes into the molar mass, and then that's how many times you have to multiply the subscripts in order to get the formula. So, okay, this was a bad slide. All right, so we're going back to the adipic acid example. We saw that the molar mass was 146 grams. So when we looked at our formula, C3 times 12, H times 1, or H times 5, and 2 times for the oxygen, we get a mass of 73.08. Well, 146 divided by 73 is 2. So winds up, there's all the directions. Oh, okay, that was bad. So we calculated the empirical formula. We know the molar mass is 146. We're going to divide the two together. We get an empirical formula for the substance that we have to multiply by 2 for. And so we get C6H10O4. Sorry about that slide. All right, so we've got empirical formula and percent composition, and then we're finding a molecular formula. There is one more example that we need to do, and they actually have done it a couple times on the AP exam over the years, so we need to make sure you guys know how to do it. But I'm running out of time on this video clip, so we're going to do part 2 of the video clip in order to show you that last example. All right, so hang tight. Go to the next part.